This is our last Friday together. Okay. Next week there's class again on Tuesday and on Wednesday. Okay, from the beginning of the end of term. Right. So today we're going to do this problem, but before I go on, I have something to announce. I'd like to apologize to Matthew and Daniel. I made a mistake, okay, in my analysis on Wednesday. Is it Wednesday? And I was in a rush. And I made the mistake, and I do apologize. The mistake I made is they were right about the what? Moment vector. Okay? You were right about the what? Moment vector. So what do you learn? Okay? About how you know. What you learn is this. I have so many years of experience, and I do make mistakes. But once you make the mistake, what do? Yeah. But before you correct it, what do? You admit that it's a mistake. Are you clear? Right? So this is not just about structure analysis. Are we clear? It's about life. Okay? I declare I did make the mistake. And I sincerely apologize to Matthew. And sincerely apologize to Dan. Dan is freaking gloating on some of the I told him I was right. He did. You could read it on his face for crying out loud. Okay? Right. So I'll tell you what mistake. I'm not going to tell you what mistake I've made, but I want you to look at the perspective of this diagram. Okay, it's not so straightforward as before. Having lunch? I'm just kidding. Right. So the internal load at a critical section along the steel shaft of a ship is calculated to be a torque of 2,300 pounds, a bending moment 1,500 pound-feet, and the axial thrust of 2,005. If the yield point for tension and shear are stress Y is equal to 100 KSI and shear Y, the subscript Y means it's at this yield. Determine the required diameter of the shaft using maximum shear stress criteria. And so that's what we're trying to achieve out here. Determine the diameter of the shaft. Right. So I'll use the same transformation that I had before. So this is example. Right. So this is so whenever you declare this is your X, this is your Y, and this is your Z. Okay. So we know the surface of concern is this surface over here. Right? That's the surface of concern. We know that if fracture will occur at that surface. And that's what we know so far. So what is given to us is we have our px. So px over here is equal to 2,000 minus 2,500 pounds. I put a minus down there because we know that this is going to go to compression. And then we are aware that we have moment about the z-axis. Moment about the z-axis is 1,500. We have to multiply by 12. Why we have to multiply by 12? Because this is in pound-feet. We have to change it into pound-inch. Okay, so this is to convert inch. So we have 18,000 pound-inch. Okay. And then the third one that we have is we have torque about X. Now this load over here that's rotating is a torque. Why? Because if we were to place our element down here, right? If we were to place an element on that axis, we know the center of interest, like what I've taught you before, the center of interest is this center over here. Okay, wrong color, Eugene. Okay, so this is our centroid. Remember, the centroid is relative to the elements of interest, yes or no? So when this is applied, the 2,300 pound-feet of torque, or we don't know yet, okay? We see, oh, it's rotating, can be a moment. No, it's a torque. When it's a torque, the green line will not deform at all. Are we clear? The green line is still the same. So this is a torque. So when there's a torque, you put this into 2,300 torque, 2,300 multiplied by 12. But this question has been very nice, okay? Too kind, it tells you that it's a torque, okay? Very nice question. So what we have in the torque is 2,000 or 27,600 pound each. So we know that failure will occur on the shaded face, right? But we also want to know the location. Yes. Because this is all in pound feet. Okay. So the location where fracture will initiate. Okay, or occur. Okay. So what I'm going to do now is I'm going to look at into the YZ plane. Okay, I'm going to look into the YZ plane. So I'm going to draw 4 elements. So the center line. Hey, come on, Eugene, seriously. So I'm going to locate the elements along this center line. Okay, so element I. Over here is element J, element K, and element L. Okay, so there are 4. So we don't know where is going to occur yet. Okay, so if we were to just focus on bending moment first. Okay, and this is where things get, I make a mistake on Wednesday. Okay, I want you all to see this. Now we are going to look at now with relative to the transformation over there. Yes. Okay. Thank you. So if you were to look on the axis now, okay, so I'm going to look on my shaft. This is our Y. And this is our X. And over here is our rotation about Z, okay, right-hand rule. So if we view at that plane, this is our shaft, okay? And if I were to put the position of element J, and then over here is our element K, and over here, this is our element I. You all can visualize, yes or no? Right? Okay. Now, Then I will have a green line here. So if we look at the moment about Z, the moment about Z is a dot over here, and it's going to comply to right-hand rule. Okay. Now, this moment vector, I put down here note, moment vector during analysis must be in the free region, not within the material. Okay. So what does this mean? Okay. You don't consider this area or this region, or this is within the what material. You don't consider within the material down here. You have to look at the what? At the free region. So this is the what? Over here is the what? Free what? Region. So when that's the case, the moment is rotating this way. So when that's the case, this is compression. This is what? Tensile. If we were to look into the material, which I did, right? So you don't look at this moment down here. This direction is wrong. Any idea why? It's within the what? Within the material. Are we clear? Yes or no? Okay. Now, if we were to view this from a different point of view, okay? If we were to view this from a different point of view. So now, what if now I'm going to view this now, where this is my Y, and this is my X, and this is our rotation about Z. Okay, now we're going to view from here now. This is our eyelid, eyelashes, okay? So what we have now, if I'm going to view from there, what do we see? We see this. Okay. Now the moment now, right? So I draw our centroid again. Okay. So the area, the face of interest, before that, it was this face that we're interested, right? It was this face. Now, when you view it the other way, now this is the face that we are what? We are interested, yes or no? And when that's the case, what will happen now? Our moment vector now becomes a what? A cross, right? So when it's a cross, you have your direction of your moment act in this way. Agree or disagree? Right? So you only have to consider the reaction or the moment vector at the what? Free what? Region. So when that's the case, this side is tension, over down here is going to be what? Pressure. Are we clear? Okay, makes sense, yes or no? Right, so you view it from any way, it will always what? Work out. Okay, right. Any questions so far from anyone? Yes. It's because if you look at the transformation, this surface over here, the shaded surface over here, and it is representing on this surface over there. Okay, if you view it this direction, then the surface flip over. Are we clear? Right. So that is out of the way. So now, we now know that moment about Z is in this direction. And this is in compression. Over here, this is in what? Tensor. Okay. So if we were to look on our elements now, I, J, K, and L, right? If we look at Px, or stress in the x direction, we know that this is Px over A, right? So for element I is minus Px over A, element J minus Px over A, element K, all of them sees the what? Minus Px over A. Okay. Now the next one, due to the bending moment, so this is equal to mz over